This video begins our treatment of the hydrogen atom. We're going to do this in 4 parts, and here in part 1 we'll focus on how we write down the Hamiltonian for this system, and we'll outline and summarize some of the key results that we will eventually derive more fully in the other 3 parts. The learning objectives for this video are fourfold: to define the Hamiltonian for the hydrogen atom, to illustrate the key features of the hydrogen atom model, to summarize the general results of the quantum mechanical treatment of the hydrogen atom, and lastly, to relate the quantum numbers n, l, and m to atomic orbitals. The starting point of our study of the hydrogen atom is to note that this is really a two-body problem. We have a nucleus with just a single proton in it that has a total mass m sub n, and is shown here in green at the origin of the coordinate system I've drawn on the right, and an electron shown in blue that has mass m sub e. As we have in the past with two-body systems, we're going to do 2 quick things here. First, we're going to move into a spherical polar coordinate system with coordinates r, theta, and phi. And we're also going to write down a reduced mass so that we can turn our two-body problem into an effective one-body problem. The reduced mass in this case, as it has in the past, is just given by the product of the 2 particles' masses divided by their sum. And if we pull up the mass of a proton, which is 1.67 times 10 to the negative 27 kilograms, and the mass of an electron, which is 9.11 times 10 to the negative 31 kilograms, we will note immediately that the denominator is essentially equivalent to just the mass of the nucleus because of the large discrepancy in the 2 masses, and m sub n simplifies out and reduces the reduced mass to just the mass of the electron. And so within a reasonable approximation, the rest of our problem case here will consider the nucleus effectively fixed at the origin, and the electron moving around it will describe that motion in spherical polar coordinates. To write down our Hamiltonian, we start by remembering that H is given by the sum of kinetic and potential energy terms, T and V. Our kinetic energy is given, as it always is, by negative h bar square over 2m times the Laplacian. In this case, the mass is just the mass of an electron, m sub e. The potential energy is given by the Coulombic interaction between our positively charged nucleus and the negatively charged electron. And so in the numerator we have E squared, where E is just the magnitude of the charge of an electron. The denominator terms come from taking the interaction between 2 charged particles in a vacuum, given a distance r apart from each other. The sign of the potential is negative here because, of course, the interaction between the positive proton in the nucleus and the negative electron is attractive. Moving into spherical polar coordinates, we rewrite the Laplacian in terms of r, theta, and phi, as shown here in the square brackets. This is exactly the same structure we have for the Laplacian when we studied the rigid rotor problem before. Using that Hamiltonian into our Schrodinger equation gives us the expression here, where now we have to solve for psi and E. Now, copying this last expression to the top of the next slide, I'm going to recognize that some terms here only depend on r, and other parts of our Schrodinger equation only depend on theta and phi. And I'm going to color those now. The terms that only depend on r are now in green, and the terms that only depend on theta or phi are in red. This immediately suggests to us that psi might be separable. And since I can't separate out terms involving theta and phi, I'll have one part of psi described by a function that is actually a function of 2 variables, theta and phi. I'm going to label that y, again shown in red. And the other function will be a function just of r, big R of r, shown in green. As we have in the past, I'll now divide by r times y. That leaves me with the expression on the screen now, where all I've done is to just simplify by canceling out y of theta and phi in the green terms and r of r in the red terms. I've also moved the energy term from the right-hand side to the left-hand side of the equation, and now I have a homogeneous differential equation. I can move the R-dependent terms to the right-hand side of the expression and keep the theta and phi terms on the left-hand side. And I can see that since the red expression equals the green expression, they must both be equal to something else, and I'll call that a constant beta. And I'll note that I've now rolled h bar square into the value that I have here for beta. This gives me two different differential equations to solve, one for what we call the angular part of the wave function, which is given by y times theta, is given by y of theta and phi, shown in red, which is equal to beta, and another differential equation to solve for what is called the radial part of the wave function, r of r, shown here in green, which in the conventional form is actually set equal to negative beta. As we'll show in the next set of videos, the result of solving these sets of equations results in three different quantum numbers, which are usually denoted by the letters n, l, and m. So to summarize some of the key results that we will derive more fully in the next couple of videos, and to summarize some of the things we've already seen, we start by noting that the wave function psi, which is a function of r, theta, and phi, is separable and can be written as a product of a radial function r of r and an angular function y of theta phi. This gives rise to three quantum numbers, and something I did not yet point out is that n's values are all integers greater than or equal to 1, and we call n the principal quantum number. L is also allowed to only be integers, but it ranges from 0 to n minus 1. So when the principal quantum number is 3, L can be 0, 1, and 2. But when the principal quantum number n is equal to 1, L can only be 0. M ranges from negative L to plus L by integers. So if L is equal to 2, then M can be negative 2, negative 1, 0, 1, or 2. Now the L quantum number is very often rewritten as a letter. When L equals 0, we usually define that as S. When L is equal to 1, we conventionally call that P. L equals 2 is usually labeled as D. L equals 3 is conventionally known as an F orbital, and L equals 4 is G, and so on and so forth. You've seen these before in general chemistry, and you've used them, I'm sure, in many other courses over the last couple of years. I've drawn what S, P, and D orbitals look like here, just so you can remind yourself of what these look like. Typically, when we write down an orbital for a hydrogen atom or other atoms, we use the principal quantum number and the L label together. So when the principal quantum number is 2 and L is equal to 1, we call that a 2p. When the principal quantum number is 3 and L is equal to 0, we call that a 3s, and so on. Now, something else that we'll derive more fully in the next couple of videos is that the energy expression is a function only of the principal quantum number. L and M do not show up in this expression at all. This is consistent with the Bohr expression for the hydrogen atom energy levels. In fact, it's actually exactly identical. Each of the solutions, again, which we'll describe in more detail later, has some number of nodes, which is always given by the principal quantum number minus 1. So a 3p orbital always has 2 nodes. A 5s has 4 nodes. A 7f has 6 nodes. And a 1s has 0 nodes. Note that as n goes up, the number of nodes go up. As the number of nodes go up, the energy goes up. So this is consistent with all of the other quantum mechanical model systems we already looked at, like the particle in the box and the harmonic oscillator. That's all for now. In the next video, we'll look at how the radial and the angular parts of the wave function are solved, and we'll see how the principal quantum number n, the quantum number L, and the quantum number m are derived naturally from the solution of those differential equations. I hope everyone's doing well, staying safe, and staying healthy. See you all soon.